I gotta make sure this only has two variables. So I need to put something in place of the z's. But there should be enough information where we can do that. So let's go off to the side here and just put some side notes. Do we know anything else about this problem?
Yeah,
They give us some information.
X times Y times Z equals to 32,000.
There you go. That number 32,000, you notice we haven't used it yet. So they gave us some information about that. They call it, you want to know what they call it? They call it the constraint. Like under this constraint, it's like, okay, they're saying that the volumes can be constrained to being 32,000 cubic centimeters. So over here is my notes. I'm like, well then I know, and I heard you say it, all right, thank you, that X volume is length times width times height. So X times Y times Z must equal
32,000.
aha. And there we go. Can't we substitute something into this? So we get this thing all in terms of X and Y, and then we can roll. Because right now it's not working because this can only be a function of X and Y, and I got these daggone Z's there. So what's Z equal to?
32,000 over XY.
Nice. Now it may look like, oh gosh, this thing's going to turn into a monster. Yeah, we'll hang with it. It won't be bad. It may look like it now. Well, we'll just, yeah, take it slow. We all know, go ahead, substitute. Here it goes. Swing around here. You're going right there. And I'm also going to put you right there. And I have yet to do this. See? I haven't even gotten to this yet. We just got to get it all in terms of two variables. All right. So now I have area equals xy plus 2y times the parentheses 32,000 over xy plus a 2x times a 32,000 over xy. Is anything simplified? Nice. So you're getting rid of these. Now I do have a function of x and y. Area of x and y is equal to xy plus pi by the y's. What's 2 times 32,000?
64.
So 64,000 over x plus pi by the x's. 64,000 over. There we go. Now we're ready. We're ready to start step 1. Get f(x). Okay, a sub x. The first with respect to x, get the first with respect to y, find the critical points. And then we'll talk about whether or not we got to do this. We're just trying to optimize this scenario here. All right. What's the first with respect to x? I'm going to call this a partial with respect to x. A sub x there. A. Take the derivative, partial with respect to x. That would just be a y. How do you do that?
Negative.
And you're good. Just think of this as x to the negative 1. Multiply the negative 1 in front. Decrease this by 1. Would be x to the negative 2, right? Did everyone see that?
Mm-hmm.
But x to the negative 2, that means where is it? So I'm going to write it down at the bottom. So I'm going to write that. Why do you see that? And you're like, yeah, we get that. I got y minus 64,000 over x squared. This should be similar. That's y to negative 1. Negative 1 times 6,400 is negative 6,400. Y to the negative 2, which means it's negative 6,400 over. Right? Oh, and this was only with x. Thank you. So I'm going to stop there. What do I set this equal to?
0.
You're the best. So when I get over here, am I going to put and? That comes up over here. So what's the partial of all this stuff with respect to y? That becomes
X
x. And then
minus.
the second part I was just writing, there we go. 64,000 over the,
Y square.
and I set that equal to 0. And now it's just an algebraic manipulation game. Can we solve the system? We try to take solve for one variable on one side, substitute it into the other side. Doesn't matter what letter you solve for, really. I can solve for y here. What's y equal to? Y equals 64,000 over x squared. Where can I put that? I'm trying to solve this system. Take that and put it where? Right there. Okay, now we got a complex fraction, so I'm gonna write this slowly. Take x minus 64,000 all over parentheses squared 64,000 over x squared equals 0. Oh, okay. Okay, maybe I'll set these equal to each other. X now equals 64,000 over a 64,000 times another 64,000, right? Over x to the 4th. Yeah, so how do you divide fractions like this? Call them complex fractions. Because you multiply the reciprocal, this comes what? Upside down like that? So I'll just draw an arrow here. You now have x equals this times this reciprocal, 64,000 times, flip it over, x to the 4th over 64,000 times 64,000. And one of these 64,000s do what?
Cancels out.
Cancel out. Just take you're out. So now x equals x to the 4th over 64,000. And we can finish that up right here. X equals 64,000 all over, whoops, x to the 4th over that. You want to play 64,000 times the x?
Mm-hmm.
I like that too. Hey, sometimes I always emphasize factoring, but I'm not so worried about factoring here, everyone, because yeah, get x equals 0. Isn't x equal to 0 solution here? But I want real life problem. Can x equal 0? So I'm not worried about factoring here. I'm just trying to get the actual number of x, the values where it's not 0. So I can divide an x on both sides. I won't lose like an important point. Cool. So that's why I'm not factoring here. But if you divide an x on both sides, that's okay, because x can't be a possible answer. 64,000 equals x cubed. How do you solve that? Yeah, cube root. What's the cube root of 64,000? 40. This problem solved. So now to get y and z, just do what? Put them in? Where do we put them though? It's a mess on this board. All right, there's y. There's y. All right, x is 40. I'll go up here, you're 40. There's x. Y is, what's 64,000 over 40 squared?
1600, right? That's 1600.
We're going to put it back in here.
40.
64,000 over 40 squared. Is that 40?
40, yep.
Now we know why in Calc 1 they told all the students in Calc 1 it was a square base. Do y'all see this? Isn't that interesting? This would happen every time, by the way. All right, and what's this? With an open top, with an open top. This is what you get. It turns into a square base. We just saw it. This is kind of neat. Where's Z? There, yeah, there it is. Right there. 32,000 x squared. 32,000 over 40 times 40. Well, that's not 40. Is that 20? Yep. Hey, what's interesting, everyone, these problems, you do every problem out of this section, I'm telling you, a lot of times you see symmetry in your answers. You see what I mean by symmetry? These came out to be what? Exactly the same. It's just really interesting. You go, what happens when you do have a top? It turns into a perfect cube. Symmetry. You know? Like 40, 40, 40. Or 20, 20, 20 in terms of the dimensions. It's really neat, but it's justified through this technique. Cool. Hey, great job with this. And what we're going to do for the rest of the class is talk about section 4.8, which is an awesome method called Lagrange Multipliers, the Lagrange Multiplier technique, that allows us to find these extremes. You might find it as a method, you go, well, we got this. And when it might be 10 times as fast or 10 times as easy to work that method. Plus, it focuses on finding the absolute, those extreme values. All right? So it's called Lagrange multipliers. Can I erase all this? Hey, cool. Hey, while I'm erasing, I'll fire this thing up. There's only one image I wanted you to see before we put the theorem down, or the whole method. Fire up. So I'm going to erase all this. They're gone. Lagrange multipliers. What is this for? You can call it the Lagrange multiplier method. You'll notice the author just writes Lagrange multipliers. You'll see by the technique. This is a technique that allows us to find the extreme values. It can be minimums or maximums, but the absolute extremes. What's the whole idea behind this? So I wanted to hit this. Can everyone see this thing? Remember I talked about the word constraint in the last problem? The constraint in the last problem was the volume x, y, z equal 32,000. Remember that? So we're like, what if you're trying to maximize some function of x and y? But there's some, but given or under the constraint of, let's call it g. So the Grange Multipliers technique says, all right, well, we're trying to see, of course, where's the highest value of f that's obtained where g intersects it. And then when you notice it's the highest number's right there. And what's that function's value, what, 10? And something else do you notice? Do you notice right here, they both share not only a common tangent. What are these two colors? Because I'm color vision. Is that red?
Blue.
Oh, this one's blue? What are these curves? They're red. Oh, thank you. I'm standing right here. I can't see these colors. So these are red, and this is blue? Oh gosh, they all look gray to me or black. So anyways, but the red and the blue, they share a common tangent, but they also share a common normal vector. Isn't that cool? And do you remember the gradient vector? So they share this common gradient vector. So the whole idea is to be vectors being parallel, you can use a what? Just multiply one by a constant multiple? And that's the idea. You take f and g, set up their gradient vectors, you set them equal to each other, but you take one of the vectors and you put just another variable in front to represent the constant multiple. Cool? But that's the idea behind this. So I'll turn this off, I'll write it on the board. It's the idea of using gradient vectors. And we'll call, everyone, drop this whole section, you want to call the constraint always letter G. Does that work? Yeah, I'll turn this thing off. Let's call it constraint G. So what we're saying is the Lagrange multiplier method is to maximize some function of x and y, let's say. It could be a function of x, y, and z. Isn't that neat? Under some constraint let's call it g of x, y, and z equals k. And when I'm just writing k like it's some constant. You know? Like think of, just to give you an example of this, in the last problem, x, y, z equaled what, 32,000? So you could have used this method to solve that problem. Or you could try it later. But this is the idea. He goes, when you take del f, and we're going to set all the corresponding components equal to del g. That'll be the gradient vector of this function g right here. But we need to multiply some variable because it'll be a constant of one of these. I'll stay consistent with the textbook. With most textbooks, they use the Greek letter lambda. So would you put a lambda right in front of that del g? Just to say that's going to be that's another constant. By golly, if you hate that variable lambda, the Greek letter lambda, you could just use a letter like m. Make up another variable, c. That's the idea. It's going to be some constant. So we're going to maximize this, and when we work the problem, everyone, you're going to make sure we're just going to set, when we get del f of this component, we'll set equal to this, we'll set this equal to this one, with the lambda distributed to it. We'll set these equal to each other, and we'll list this constraint G. And all we gotta do is solve that system. And it's pretty neat because this makes a lot of problems way easier to solve. Okay? So, and let's start with one. This is from the textbook. And when you find the point, on the plane x plus y plus z equals 1. That is the shortest distance. From, they get another point. 2, 0, negative 3. And we're going to do 2 problems. We'll start with this one. Hey, could have I used section 14.7 to solve this problem? Absolutely. I want to point that out. The last section. We just got to know distance formula to get this thing started. Do you all agree? Find a point on a plane that is the shortest, there it is, distance from this point. Don't we need the distance equation? That's the function that we're trying to actually minimize. What's distance formula in three-dimensional space? So we can call it D for distance, right? Here's my f of x, y, and z. What's distance equal to? Square root of what? X1